Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello friends, in the last lecture we have studied about the methods of preparation of the benzene derivatives, and in that case we have got to know that mostly we are getting a monosubstituted benzene. So what happens if the monosubstituted benzene is further being substituted by another group? So let us talk about that. So now we are actually doing a study of what is the influence of the substituents present in the monosubstituted benzene. Because in the previous lecture that we have got to know that the product that we have got by using the various methods so as to prepare a benzene derivative, in that case we have got to know that the derivatives or the product that are being formed are basically monosubstituted. So what if happens that if we make another product, even that is the monosubstituted benzene of the product that we have. So that is what I am going to talk about is if a monosubstituted benzene is again further undergone through a substitution reaction. So what would be the possible product? Obviously there are three isomers that we could get. Either we could get an ortho isomer, para and meta. But which one would be present in more quantity or which one would form in a more quantity, as well as what would be the reactivity of that monosubstituted benzene for which it will allow the other reactant to get attached to it, to the benzene, or what would be or which position would be the other group that would be attached on the monosubstituted benzene. So this all are the parameters that we have to study, and that is what we are going to study about this thing, that is what is the influence of the substituent that has been present in the monosubstituted benzene. So now this monosubstituted benzene or this substituent that has been attached to the benzene, it will depend on its nature, that it will allow which group to be attached on the carbon atom and at what position. So this determines the reactivity as well as the orientation of the other group or the other substituent that is been going to attached on the monosubstituted benzene. So that is what we are going to talk about in this lecture. So for that I have a few details that which would increase the reactivity or which would decrease the reactivity. So what are those kind of substituents or what are those kind of groups are called? So let us talk about that also. So basically the substituent that makes the ring more reactive than the benzene is called as activating group. So that is what I am going to say. That is, when it comes to benzene, then benzene is basically known as a stable compound and that undergoes substitution reaction, and that also moreover electrophilic substitution reaction, and it doesn't go the process of addition reaction very easily. So the benzene is a quite reactive substance when it comes to the substitution reaction. But what if a monosubstituted benzene is being present? That is, if one hydrogen of the benzene is being replaced by another group, that is, I am talking about a monosubstituted benzene. So is that making the benzene more reactive or that would make the benzene less reactive? So depending on that, what we have got to know that the substituent that is being attached to the benzene ring, that will make the benzene ring or that will make its reactivity more than that of the benzene, then that kind of group that influences to make its reactivity more is basically known as activating group. So as the name suggests, activating group is nothing but it will activate or it will be more reactive compared to that of the benzene. Now moving to the another one, that is, what if the substituent that makes the ring less reactive than benzene? So even there are certain substituents that will make the benzene ring that is less reactive, so as that would be called as deactivating group. So that is the reason that that would be the ultimate, the monosubstituted benzene that would be less reactive compared to that of the benzene, and that kind of group that are been attached to the benzene, and that makes the monosubstituted benzene less reactive than compared to that of the original benzene, and that kind of groups are basically known as deactivating groups. So now we are going to deal with these two informations, that is these two groups basically, that is activating group and deactivating group. So what are this activating and deactivating group? We have to deal with another study, that is basically the isomers that would be formed, because a monomer that has been present because the substituent that has been present on the carbon atom of the benzene, and we could see that that group will allow the other groups. Suppose if the whole monosubstituted benzene is undergoing another substitution process or another substitution reaction, so that group will decide that the other group should be attached on which of the carbon atom, that is the position of the carbon atom. So that is what we are going to talk about. That is, I am going to talk about what is actually ortho, what is meta position, and what is para position. So let me recall it again. That is, suppose if we have a group that has been attached to the benzene. So this is the group that we have, and it is not necessary that I should write the group over here, because the numbering will start from that carbon atom only where the group is been present when it comes to the monosubstituted benzene. So suppose if a group like X is been present, and this X is not highlighted, this is just an element that I've represented over here. So suppose if the other group, or suppose if this monosubstituted benzene is undergone another substitution reaction, and if the other group named it as Y, suppose, if that Y is or that group is being attached to the adjacent carbon atom, and this is the one that would be named as carbon number 1, this would be carbon number 2, and this is carbon number 3. So the position where the Y has been attached, it is the second position, or it is the adjacent position of the carbon atom over here where the substituent has been attached. So therefore this kind of groups are basically called as ortho groups, and this is basically the ortho isomer that we have got. So what if we say that the group is attached on this third position, and I will name it as Y. So now as we could see that there is a substitution process in which one carbon is not being substituted, and you could see an alternate after that. An alternate carbon has been substituted, and that's the reason the number of this is basically 3, the third carbon atom. So this kind of group that are been attached over here, that is on position number 1 there is X, and on position number 3 there is Y. So therefore this would be called as meta. And ultimately, suppose if on the fourth carbon atom or on the opposite carbon atom, suppose we could see a group Y is been attached, then that would be called as basically para. So let me introduce this thing so as to make it clear. That is, if a disubstituted benzene which is present in this way, so basically they are present in ortho position, that is carbon number 1 and carbon number 2. So therefore this is known as ortho isomer. Talking about the another one, if it is present in this manner where its alternate substitution has been happened or by on the alternate carbon atom, so therefore this is called as the meta isomer. And in this case, suppose the Y has been attached on the fourth carbon atom of the respective carbon atom over here, so now therefore it will be called as a para isomer. So in the 3 cases, that is, these 3 are basically the isomers, that is, one is ortho isomer, meta isomer, and para isomer. The only difference is, yes, the position of the substituent or the position of the Y substituent, and that makes the and that makes us to decide that which one should get a more priority while forming a product. So that is the main reason that we are going to talk about, that which group, that is this group, that is X, this will decide that the substituent, that is Y, that will attach on which position, and that will increase the reactivity of the benzene of the product or not. So that is what we are going to study about. So for that we have got to know another thing, that is a group that causes electrophilic attack to occur mainly at ortho and para position are called as ortho and para directing group. So in this case, suppose if I will explain you this thing, suppose if the substitution, electrophilic substitution has occurred in such a manner that because of this X that has been present in the benzene, and after the reaction has been occurred, then we could see that the product that have been formed is ortho and a para isomer. So this is possible because this group that has been attached to the benzene, this will direct the electrophile like Y to attack on the ortho position of the benzene or of this group, or on the para position of this carbon atom, as you could see over here. So this kind of groups that will influence the other substituent to attack on their ortho position or attack on their para position are basically known as ortho and para directing group. And now talking about the another one, suppose a group that causes electrophilic attack to occur mainly at meta position is called as meta directing group. So suppose if the substitution occur in such a manner that depending on this X, actually it's all dependent on the substituent that has been attached to the benzene, that is the monosubstituted benzene. So if that will influence that the other group that has been going to attach, that is the electrophile that has been going to attach to the benzene, if that attacks on the meta position, then that kind of group is basically called as, this group will be called as a meta directing group. That means it will influence the other group to attack on the meta position of the benzene. So that is what we are talking about. So to understand the reactivity of this monosubstituted benzene and the orientation that will allow the other group to be attached on the ortho, meta or para position, we have to understand the resonance, and that is the inductive effect of the group that has been attached to the benzene. So this two studies that we are going to do, that is the resonance effect and the inductive effect. So based on that, that will allow us to understand that what kind of the substituent that will allow the molecule or the product that will be more reactive or less reactive. So depending on that, we are going to study about the substituents. Are basically classified into three groups. That is the group that has been attached to the benzene, and that will allow the overall product to be more reactive or to be less reactive. So that is the thing that we are going to see here, and that will allow the other group to be attached on which position. So that is what we are going to study in this case. That is, they are being classified into three groups, that is activating and orthoparadiating group. The second is deactivating and orthoparadiating group. The next is deactivating and meta-directing group. So let me talk about this in a brief, and we are going to talk about this in detail also. So talking about this kind of groups, that is this kind of the groups that is activating as well as that is ortho and para-directing. So basically these are the groups that will make the product, or that will make the monosubstituted benzene more reactive. And that's the reason that it will, suppose if that is more reactive, then the position of the other substituent group that will be on the ortho and the para position of the monosubstituted benzene, and that makes us to understand that the overall product, that is the monosubstituted benzene, will be more reactive, or that will be allow the other substituent to be attached on the ortho and para position very easily. Talking about the deactivating group, as we have studied earlier also, that will be a kind of monosubstituted benzene that is less reactive than that of benzene, and moreover it will allow the group to be attached on the ortho and the para position, and that is what we are studying here. That is that kind of groups that would be attached on the benzene, or when we are talking about a monosubstituted benzene. So there are also kind of groups that are basically deactivating and ortho-para-diating group, means that they are deactivating as well as they will allow the other substituent to be attached on the ortho and para position. And talking about the last one, that is deactivating and meta-reacting group. So basically these are the products that will deactivate that will reduce the reactivity of the benzene and of the product compared to that of the benzene, and in that case that will allow the other molecules or the other groups to be attached on the meta position, and that's the reason they are called as meta-directing group. So now let us talk about each one in a brief and let us understand. So talking about the first one, that is activating and orthoparadiating group. So therefore there are certain groups that will activate the benzene ring and therefore increase the reactivity of the benzene ring, or increase the reactivity of the product that has been formed as in monosubstituted benzene. So what are those groups? Those groups are basically, I'll give you a few examples over here. Those are basically alcoholic group, or like OH group, and somewhere it is NH2 group, that is it can be a primary amine group, secondary amine group, and talking about the another one, that is this OR, that is for the ether. So even that is a kind of the group that would increase the reactivity of the monosubstituted benzene, and moreover we could see that even that is an alkyl group will also activate the benzene ring and making the other groups to be attached on the ortho and the para position. So these are the few examples, or these are the few groups that I was talking about, and for which let me give you a detail about what happens when a benzene is attached with an OH group, or when we are talking about phenol. So talking about that one, and in this case I will show you that why the reactivity is being increased, and why the other groups has got a position of the ortho and para so as to get attached over there. So let me give it a small detail about this monosubstituted benzene like that of phenol. So this is the structure of phenol, and what we know is, as because it consists of basically two lone pair of electrons, as you could see over here on the oxygen atom. So there we could see that the resonance is not only till the ring, it will be on this between this carbon atom and this oxygen atom also. So therefore phenol is basically the hybrid structure, the resonance structure that we are going to see it now. So therefore what will happen is, suppose if this two lone pair of electrons, if this jumps on this carbon atom, so what we could see that this lone pair of that this pi electrons, they will shift over this carbon atom, so making it to be having a resonating structure of this one that I am going to draw now. That is where we could see that because of this two electrons that has been deposited on this carbon atom, making this carbon atom to be more negative. And meanwhile we could see that the oxygen and the carbon atom would acquire double bond, and this makes the oxygen to acquire positive charge. The reason behind that is because this two electrons has been jumped over between the atom of the oxygen and the carbon, making it a double bond. So therefore this would be basically a positively charged oxygen atom or anion. And talking about the rest of this, that this double bond and this double bond would be unaffected, so therefore I would write it over here as it is. But this is a resonance that I am going to show. So therefore what will happen is, even we could see that the double bond would be shifted over this carbon atom, and this pi electrons would be shifted on this carbon atom, so making the resonance structure to be this one. Where in this case basically the double bond has been shifted over here, or this two lone pair of electrons one lone pair of electron has been deposited on this between this carbon atom, making a bond over here. While here we could see that the negative charge has been obtained, and this was been unaffected. So this is what the residual structure that I am drawing. And meanwhile talking about this one, this will remain as it is for a while, making this to have basically a positive charge. So again what will happen is, again the resonance will, or the shifting of the pi electrons would take place, and in this case what will happen is, we could see that this pi electron has been shifted over here and making this pi electron to be shifted over here. So therefore the product that we have got, we could get in this manner, will be this one that I am writing over here, where the double bond in this case would be the same, the position would be same. Here it is, where here there is a double bond formation that we could get, and here basically there would be a negative charge over here, so I would write it in this manner, and ultimately this would be the same thing, and that would be unaffected for a while. And meanwhile, so as to complete the resonance, what I will do is, I will shift this electron to this carbon atom, and again this electron will be shifted on the oxygen atom, making this to be formed as a product like, or to form a structure like. So this structure is very similar to the first one that we have drawn over here. So basically this is showing that the phenol has a resonating structures, as you could see over here. So now the more detail that I am going to talk about. Yes, that why this is actually an activating group, as well as it is ortho and paradiating. So as we could see that basically the electron density in the benzene is now been reduced. The reason behind that is the electron density, that is because of the pi electrons, as you could see that it has the pi electrons that are been present in the benzene ring, and since OH is the one that is inductive, that is the group that is showing electron withdrawing group, that is basically electron withdrawing group, and that is the reason that we could see that because of that the electron density of this would be going on decreasing overall. As you could see over here, even here also, that is that here there are basically 6 pi electrons in the ring, and here as you could see there are basically 4 pi electrons, so making the electron density to be reduced in the benzene ring. And meanwhile if you say that electron density is being increased in basically in the ortho position, as you could see this is the ortho position. Suppose if this is the group that has been attached on this carbon atom, so this is basically the electron density that has been increased, not in the overall benzene but in this on this carbon atom. That is in ortho position, you could see an electron density which has been increased, and meanwhile On the para position also you could see that is the electron density has been increased, and again on the ortho position you could see the electron density has been increased. So this is the resonating structure that we have got to know, that because of the resonating structure we have got to know that the electron density on this carbon atoms, that is on the ortho position and on the para position, has been increased. And meanwhile we could see that because of which, that is, this is the negative charge that has been acquired, so this will allow the other electrophile that is being going to attach, or that is being going to substitute on this phenolic ring. So in that case that would be very much easy, so as that would be attached on this carbon atoms that is on the ortho and the para position. So that is the reason that we have got to know that at ortho positions and at para positions, that we could see the electron donating tendency, that is electron donating tendency to the electrophile that is going to be attached, it is more, and that's the reason it is more reactive towards the electrophilic substitution, towards the ortho position and towards the para position. So that is what we have got to know here. And now let us talk about the another one that we are going to talk about, that is the second one, that is nothing but deactivating and ortho and para directing group. So talking about the earlier one that we have made a study on, in that case we have got to know that it's basically the OH group, or certain kind of groups that were being attached to the benzene so as to form a monosubstituted benzene. So they are basically electron withdrawing, but they are not that much electron withdrawing. Basically they are basically weak electron withdrawing groups. And now what we are going to talk about is deactivating groups. And these deactivating groups are stronger withdrawing groups. So for example, if I would talk about the groups like fluorine, fluorine group, or chlorine, bromine, or kind of halide groups that we know. So suppose if this is the groups that are being attached on the benzene, so therefore this has the capacity, or this groups has the capacity to withdraw the electron from the carbon atom, making this to have basically an electron withdrawing inductive effect. So because these groups are basically more electron withdrawing and show electron withdrawing inductive effect, that is the reason that what will happen is the resonance that we have saw over here, that is the negatively charged donating effect that we could see on the ortho position and on the para position. So in this case, suppose if any of the group that is been attached on this position like F or fluorine or chlorine, bromine, or any kind of halide, so what will happen is the electron would be withdrawn, and in this case where we could see that the position or the electron withdrawing effect that has been shown by this positions of the, that is ortho and para, will become less. And suppose if this become less, then ultimately we could say that the electrophile, which is basically positive in nature, that won't attack more easily to the less negative ortho and less negative para position, and that makes it to be less reactive. Means suppose if we have an fluorine group that has been attached on the benzene, that is we are talking about fluorobenzene, so that makes it to be very less reactive than compared to that of the benzene, and that won't allow that much reaction, or that won't allow any of the substituent to be attached on the ortho position and para position easily, and that makes it to be, yes, that makes that to be a deactivating group. So therefore that deactivates the benzene ring, and that's the reason the substitution will happen, but not that much ease, and the substitution might be happen at the ortho and para position, because this will remain the negative one, but it won't be more negative, it will be less negative. And meanwhile electrophile which are positive, so there is a possibility that they could attach on the ortho position as well as on the para position. So that is the thing that we have discussed over here, that there are certain groups they are deactivating, but yes, they are ortho and para directing groups. So therefore they will allow the other molecules also, or the other substances also, to be attached on the ortho and para position, but they makes the ring, or they are less reactive compared to that of the benzene. So this was the second one that I was talking about, and now let us talk about the third one. And the third one is deactivating and meta directing group. Yes, there are certain groups that are basically, they will deactivate the reactivity of that is the monosubstituted benzene for the electrophilic substitution. But meanwhile, they are not as usual that we have got to know that most of the electrophile they attack on the ortho position and the para position depending on the substituent that has been attached on the benzene. But now this kind of groups they will allow the electrophile to be attacked on the meta position, and meanwhile the overall the reactivity would be less, making this to be called as deactivating groups. This would be the deactivating groups. So there are certain groups that I am going to discuss about, and those certain groups are basically nitro group like NO2, cyano group or cyanide group like this one, carboxylic group that is COH, and let us talk about the another one that is aldehyde group also. So these are the certain groups that are basically known as deactivating groups, and they will be meta-directing groups toward the other substituents that are going to be attached. So let me talk an example related to the benzene and this nitro group that we have mentioned over here. So suppose we have a group like a nitrobenzene. A nitrobenzene can be written or can be expressed in this way. So this is the structure that is of a nitrobenzene that we have, and this groups that we have that is a nitro group is basically an electron withdrawing group, and that is the reason because of which that is basically that is just like the groups like fluorine, it makes the benzene ring to be less reactive and making that to be basically deactivating group, and that's the reason that the overall reaction is basically having a less reactivity towards the electrophilic substitution. So similarly, this is the group that we have. So what will happen, even here we could see that the resonance is been possible. So therefore the resonance will be possible because of the pi electrons that are being present over here. So therefore these are the electrons that are being present, and suppose if the shifting of electron would take place over here, then we could see that this electrons would also shift on this nitrogen between nitrogen and this carbon atom. So here we could see carbon-carbon double bond. So the structure that are going to be possible that are going to form, or the hybrid structures that are going to be formed, are basically here because of the nitrogen that is been present here, and because of the oxygen is also been present here, while the oxygen has got a negative charge. So therefore we could write it in this way. Well, this negative charge has been gone on this oxygen atom, making there should be formation of a double bond. That is what I am observing over here. So now we could see that this is the double bond that has been already present over here. And meanwhile, we could see that if this double bond has been shifted, or this kind of electrons that has been shifted so as to form a double bond between nitrogen and carbon over this carbon atom, so therefore this will be now turned into a positively charged carbocation, as we could see. So now, so as to make this to be stable, so what will happen is again this shifting of electron would take place in such a manner that here we could see a positive charge. So therefore the resonating structure that we are going to observe here is, in this case, because of the double bond of this carbon atom is the same, here it is. So I am making this a no change, and because of which here we could see that the nitrogen is the one which consists of two oxygen, where one oxygen is basically more electronegative, in this case because of the shifting of electrons. And now here we could see a formation of a double bond. And if there's a formation of a double bond over here, then the electron density will on this carbon atom will get reduced. So now I could say that here I could see a positive charge. But so as to stabilize this as a, or so as to neutralize this carbocation, so what will happen is that is the bond shifting would take place from on this carbon atom. So therefore we could see that this would turn into a positive charge. So let us conclude this one by drawing the resonating structure. So therefore this is the resonating structure that I am going to represent, where the double bond of this carbon atom will remain the same, while here I could see the double bond has been introduced. Meanwhile, this electron that has been shifted on this carbon atom, and here the electron has been less, making this position to be more positive. And talking about the nitrogen atoms, the nitrogen atom was as it is. There will be no change in that. And ultimately, so as to neutralize this one, basically or this carbon atom which is basically positive, so we could see that again the shifting would take place in such a manner that that is this shifting would take place in such a manner that we could see that the double bond has been regenerated on this between the carbon and between this nitrogen. So therefore we could see that the resonating structure consists of a double bond over here, again basically a double bond over here, and here also we could find a double bond, and ultimately it consists of a nitrogen over here. So this is how we could get these are the resonating structure that we are going to get, and ultimately we will get the same thing that we have observed over here. So therefore, and yes, meanwhile the double bond would also be present over here, so as the shifting would take place in such a manner. So that is what we have got to know over here. So this is basically the structures that we have got, and here we could see that the resonance is possible. The resonance is possible, but the thing is, if you could see on the ortho positions and on the para position, here there is less electro density. And if we compare it to the ortho position and now to the meta position, we could find that meta position has more electrons, or there is no affected electron density, and comparatively we could say that the meta position is the one which consists of more electron density, and that will help the electrophile to be attacked on the meta position only. So that is the reason, even though it is being a deactivating group, that is the nitro group is a deactivating group, and but the position where the electrophile would be attached on this overall molecule will be on the meta position, and that's the reason that it is a meta dieting group. That is NO2 group is a meta dieting group, and a deactivating, it will deactivate the overall monosubstituted benzene towards the electrophilic substitution. So this was the three kinds of the thing that I wanted to explain to you, that is activating ortho and para position, deactivating ortho and para position, and that is deactivating meta position, or this is what I have wanted to explain to you. And talking about this one, that is the first one that I have explained. Here also we could see that the electron density of the benzene ring has been reduced, and similarly here also the electron density was been reduced. But the thing that I have observed, and we have all got to observe, is because of the electrons that are being present over here, that is on the or electron density that is being present on the ortho position and para position is more compared to this one. And that's the reason, in terms of an activating group and an ortho position and para position attachment, we could see this OH plays a very important role, and that's the reason that we could get the products that are basically monosubstituted benzenes that we could get at ortho position and on the para position, while here the meta position would be occur, because the density here is comparatively more compared to that of the ortho and para position over here. So that is what I wanted to explain you. So thank you friends for watching this video. I hope you have understood this video very clearly, and will share this video with your friends. So thank you for that, and yes, don't forget to subscribe to Ekeeda channel. Thank you so much.